Welcome, welcome. So today we officially enter the second half of the semester and we are starting on our magnetism topic. So remember, it's electricity and magnetism. They're very similar and related in some ways, and they're also different in some ways. So what we're going to do today is we're going to start talking about magnetism, what it is, magnetic forces, magnetic fields, and then we're going to stay with magnetism basically for the rest of our semester. Okay, so I'm going to start by kind of just introducing what magnetism is and then drawing parallels between how does it relate to electricity? In which ways is it similar and in which ways is it different? Now, we already heard the word field, so in that case, there's a similarity. It is at a distance force, so there's going to be a field associated with it, just like the electric field, but mathematically, it's going to be different. So let me get my notes up. Okay, so here we go. We have topic 7, magnetic fields. Welcome to the second half of our semester. So when we think about magnetism, think about a magnet, like a little bar-shaped magnet that you would put on your refrigerator door, or I think we all have an idea of what a magnet is. Well, so when we talk about magnetism, kind of always start there. And magnets have a north and a south pole. And those poles are going to repel each other if they're two similar poles, and they're going to attract each other if they're two different poles. So think of it as our positive and negative charges. But instead of calling it positive and negative, we like to call them things like north and south. It's still going to be one positive, one negative, but we give it different words like north and south. So the north end of a compass is a magnet. Okay, so a compass is really just a magnet, and as that little needle, the little compass needle moves around, it's going to align with Earth's magnetic field. So Earth has a magnetic field, and we're gonna see that in a couple movies right now. Earth has a magnetic field that comes from its molten core. So we'll see later on throughout the whole semester kind of what creates magnetism. Well, moving charges. I mean, the summary is moving charges. So if you have a molten core, a core of this ionized plasma-y soupy stuff that's at the center of our Earth and it's spinning around, you have moving charges and we create a magnetic field. And Earth's magnetic field is actually reversed from what we think. Earth's magnetic field has geographic north, right? So the North Pole, out by Greenland and Iceland and all of those, is actually magnetic south. And then likewise, the South geographic pole, where Antarctica is our magnetic north. And that's why a needle on a compass lines up to geographic north, because the north end of the needle is being attracted to the south end of Earth's magnetism. Now, one thing to note is when we're looking at this picture right here, and that's Earth right in the middle, or a bar magnet, or anything like that, we see that we have magnetic field lines that have a directionality associated with them. They come out of the north side of the magnet and in to the south side of the magnet. We'll come back to that. So I always like to kind of put side by side parallels of what we've already learned and then add new stuff. So we've already learned about the electric field, how it goes radially outward from a positive charge, right? Because we ask ourselves, how would a positive charge react when placed near the one setting up the field? Well, it would be repelled, so it would go radially outward. And we've also seen that for a negative charge, it goes radially inward, because we ask, how would a positive charge react? Well, it would be attracted to it. Well, for magnetic fields, what does that look like? What does it look like for magnetic fields? Well, magnetism always has a positive and a negative together, or a north and a south together. And the magnetic field lines connect. They go from positive into negative, from the north into the south. Now, the funny thing about magnets is if I cut a magnet in half, I am not left. So let's say I take this magnet and I cut it in half. I'm not left with a north half and a south half. That's not how it works. I'm now left with two small magnets, each with north and south. Interesting. And that is called the magnetic or the absence of a magnetic monopole. These are monopoles, single pole, single charge. Magnets will always be dipoles, north and south together, north and south together. If I cut it, now I have two magnets, each with north and south. But magnetic field lines, we see they always connect. They always connect and come back upon themselves. So we can see that there's similarities and differences. Here's a little GIF, and you have access to these on Canvas. And what we have is a magnet, a very strong magnet. And then down here are these little, like little filaments, like little iron filaments or any ferromagnetic material. You could do this with a shaved pencil, pencil filings from the lead, and a magnet. So let's see this. In slow motion, you can start to see the B fields, how they curl upon and come in from north to south. And you have access to this, and you can pause it and rewatch this, but it kind of shows the shape of those magnetic field lines. Okay. So first of all, the magnetic field, we're going to denote with letter B. So everything electric is E and everything magnetic is B. I'm not sure why B, but it just is. So the fields always go in the same direction. And so in that way, it's a little bit easier than the electric field because it always goes from the North Pole into the South Pole. Just remember that for Earth, our magnetic north is in our geographic south. So the magnetic field lines go from the South Pole to the North Pole, from the South geographic pole to the North geographic pole. But we want to know, okay, if there's a magnetic field, what does that tell us about magnetic forces? Okay, so we're kind of working our way into, first of all, describing the field, and second of all, understanding how that creates forces, just like we did with electricity. So for the magnetic field, the magnetic force says something like this. You have to have a charged particle interact with this field, but not only that, the particle has to be moving through this magnetic field. And in that case, if we have a charged particle that is moving, then we get a magnetic force. For electricity, we just needed to have a charged particle interacting with the field. Now we need a charged particle moving. And not only that, but it has to move in a particular way. And we'll see that. We're going to start talking about cross products. So we say moving charges create magnetic fields. Okay. So where does magnetism come from? It comes from moving charges. So the magnetic field lines go from magnetic north to magnetic south, which means that it goes from geographic south to geographic north on Earth. Okay, so if we're talking about electric and magnetic fields, so everything electric is E and everything magnetic is B. So the electric field exerts a force whether or not the charge is moving or at rest, right? All I need is a charge to come in to that field. And for a magnetic force, a magnetic field, there's going to be a force only if it's moving, first of all. So here's my charge. Well, now it has to be moving. There's a velocity vector. And wait a second, it has to be moving non-parallel to the B field. So this moving charge has to interact with that B field in such a way that it's moving non-parallel, which gives us a cross product. So a dot product deals with parallel components of the vectors. So this is for dot product. And a cross product deals with perpendicular vectors. So moving non-parallel. In other words, we want the part of the velocity that is perpendicular to the B field. We're going to see all of that. But for now, let's just say, wait a second. To get an electric force, all I need is a charge to come into the E field. Done. There's a force. Wait, with magnetism, I need a charge, and it has to be moving, and it has to be moving in a non-parallel manner. Then I get a force. If it's not moving, no force. If it's moving parallel, no force. So with the E field, there was always going to be an electric force as long as the charge comes in. With the B field, we can have a charge and still not have a force. Okay, so that's the first part, and that kind of relates directly to our equation down here. Okay, the second part says the E field at some point E, that's our newtons per coulomb, our force per unit charge. And we always define it by asking how a positive test charge would react at that point. So that was a little bit complicated for the E field. Well, for the B field, it's related to the force exerted on a moving positive test charge. But also the B field just goes from north to south. Okay. Electric fields come from charges, whether they're moving or not, but basically if a charge exists, it creates an E field. A B field, you have to have that charge, and that charge has to be moving. So you might be asking yourself, well, if I have a charge and it's moving, does it have both an E field and a B field? And the answer is yes, it does. And that's why the semester is electricity and magnetism together. So let's separate out right now and just focus on this part. It's going to come together. So the magnetic force is a cross product. That means that we're multiplying two vectors and getting a resultant third vector. Cross product is a vector product. Dot product is a scalar product. So the directionality for the magnetic force is going to come from using something that we're going to call the right-hand rule for vectors. But right now, let's look at just the magnitude, just the strength of it. Okay. All right, so let me open up a whiteboard and start from our equation. So we have that the magnetic force is equal to a charge and then V cross B. Okay, so first I want to do this cross product. So this says we have a charge that is moving and is moving in a non-parallel manner. So let's do cross products. Okay, the magnitude of any cross product, so let me change colors. The magnitude of any cross product, A vector crossed into B vector, is A magnitude, B magnitude, sine of theta, where theta is between A and B. So it looks at the perpendicular components, because that's where the sine theta comes in. Right, so it would look at the perpendicular component between A and B. That's for the magnitude. And that's just the definition of a cross product. So if we want to look at our magnetic force, so our magnetic force magnitude, well, the charge is hanging out, and then I've got magnitude of the velocity, magnitude of the B field, and then sine of theta. And I always like to remind myself, theta between what? Between the motion and the B field. So that if it's moving parallel, so that the velocity is in the same direction as the B field, theta is 0, and sine of 0 is 0. So parallel gives no magnetic force. And what about perpendicular? So now if the B field points this way and the velocity points that way, sine between them is 90, and sine of 90 is the greatest value, 1. So perpendicular gives you the maximum magnetic force, and parallel gives you 0. So you can have a charge moving with the exact same speed, and in one direction, it'll have 0 magnetic force. Right here, if it moves parallel, it'll have 0 magnetic force. But if the particle moves perpendicular, it'll have the maximum magnetic force. Same charge, same speed, just change the direction. Okay, so go back to our slides here. Let me come back to our slides. Here we go. So that's where this, let me get my pen up. That's where this comes in. QVB sine theta, where theta is between those two things. And this is magnitude, right? So magnitude is always positive. So I'm putting in the absolute value of the charge. Magnitude V, magnitude B, sine theta. Let's look at the units real quick. Okay, so the units of the B field, not of the force. We know the units of force. Force always has units of newtons because, you know, Sir Isaac. So let's look at our units on this Tesla here. Magnetic force has units of newtons. Magnetic field has units of Teslas. So what is a Tesla? Well, if we want to solve here for the magnetic field, we're going to get the magnetic field is equal to the force over QV sine theta. So the units on, oops, let me undo that. The units that go in here are going to be, I've got newtons in the numerator, charge is a coulomb, a velocity is a meter per second. And we call that a Tesla. So here it is. Right, and that just comes from working with this equation and solving for my unknown for the B field. Okay, but I see one relationship here. I see coulombs per second, and a coulomb per second is an amp, right? Moving charge gives us current. So I can also write it as newtons per amp meter. Sometimes Instead of using the units of Teslas, you'll hear the unit of Gauss, and those are related via a 10 to the fourth. So 1 Tesla is 10 to the fourth Gausses. So that is the magnetic force magnitude. Magnitude, always positive. How do we find the direction? Okay, so we see that with the cross product, we have to have a charged particle. It must be moving in order to feel a magnetic force on it, but not only that, but how it moves matters. So perpendicular will have a maximum and parallel will have a zero force. And the force, the direction of the force, well, we need to understand where the direction is. So the magnetic force direction. So we've already looked at the magnitude. Now let's talk about the direction. So we're going to talk about a right-hand rule, but there's going to be plenty of right-hand rules coming your way. So this is going to be right-hand rule number 1. So a right-hand rule is a tool to find the directionality of a cross product. And there's many ways to do these. Engineers have a little bit of a different convention than mathematicians, than physicists. But we all get to the same result. That's the important part. There might be different methods, but we all get to the same result. Okay, so because of that cross product, we know that the magnetic force is always going to be perpendicular to both V and B. So for example, if our velocity and B field vectors lie flat on this plane, like flat on your table or on your piece of paper, then that means that the magnetic force is either going to come straight up from the table or go straight down onto the floor, right? So if V and B are flat on your table, the magnetic force has to be perpendicular to it, which is either straight up or straight down. So we're going to use the right-hand rule number 1 to find the direction of the force. What does that say? It says point your fingers in the direction of the velocity and then curl your fingers in the direction of B. I always like to say kind of align your palm in the direction of B. And you curl your fingers and you stick your thumb out, and wherever your thumb points, that's the direction of the magnetic force. Okay, so let's do this. So we have a velocity that is, flat on your table. So pointing to the right, flat on your table. Okay, so we're going to do this. We're going to point to the right and point your fingers to the right. Doesn't matter how you're facing your palm yet. We're not doing that. We're just doing the velocity. So the velocity says take your fingers and point it to the right, flat on the table and to the right. Now, curl your fingers in the direction of the B field. So we're going to say the B field is straight in front of you. So curl your fingers in the direction of the B field. That means I'm going to take my palm and I'm going to point it straight in front because that's the way the B field goes. And I'm going to curl my fingers, which are still pointing right, and I'm going to curl them towards in front of me, which is where the B field is. And I'm going to get a magnetic force that points straight up. Let's do this again. Let's imagine our velocity's to the right. So point your fingers to the right, flat on the table and to the right. But now your B field points towards your back. So now take your palm and point it towards your back, curl your fingers in, and now you have a magnetic force that points straight down. We're going to practice this, and it's going to be a little bit complex to do with this video. So please, please, please come ask my office hours. Go to the online tutoring that is on my Canvas page. This right-hand rule stuff can be a little tricky. So let me get a screen back up. We're going to do some examples and kind of walk through this again. Okay, so fingers point in the direction of the velocity. Then you kind of turn your palm so that you can curl your fingers into the B field. And whichever way your thumb points, that's the direction of the force. Let's do some examples to kind of see that in action. Oh, actually, before we do that, this is a great time to maybe pause. Go watch these two little clips on Canvas. You have the on Canvas you have the links. Okay, so let me actually show you. Oh, I don't have it. I don't have it open. But they're little like 5 and 10 minute clips, I think, about how the Earth gets its magnetic field, talking about that molten core, and then also the how aurora borealis or northern lights work, and also there's also southern lights, not just northern lights. Um, we get them at both the North and the South Pole, but our world is highly North Hemisphere centric. So most of the narrative we tell is a Northern Hemisphere narrative, and that's why you hear Northern Lights a lot rather than Southern Lights. But yes, they happen in both poles equally. So when you're watching this clip, just remember it's not just heading north to see aurora borealis. You can also head south to see them. Okay, so great time to pause, watch a little movie, and then come back and we'll do some examples with the right hand rule. Okay. Oh, I missed something super important. Our right hand rule is set for a positive charge. If we're going to do a negative charge, we have to flip our result. So let's do again this example here with the velocity pointing to your right, the B field pointing towards your front, like wherever you're facing, and finding which way the force goes, except this time let's do it for a negative charge. So we're going to do the exact same process, but then at the end, whichever way our thumb is pointing, we're going to flip it. So we still have velocity to our right. So point your fingers to the right, and it doesn't matter which way your palm goes right now because that's the B field. So just start with velocity pointing to the right. Now, let's just say the B field points straight like the way you're facing. So now take your palm and point it that way, the way that you're facing. My palm is pointing the way that I'm facing. And now I can take the velocity, my fingers pointing to my right, and curl them into the B field, my palm pointing straight forward. And I get that force that points up. And that's the way the force would point for a positive charge. But wait, this is a negative charge. So what I'm going to do is I'm going to do the exact same process. And then I'm just going to go, oop, that way. Do not try to do everything backwards. Do not try to do a left-hand rule because it just doesn't work. Do everything like you would for a positive charge and then just flip it. Okay? So let's do two examples, one with a proton, a positive charge, and then one with an electron, a negative charge. And we'll see how to use those right-hand rules and directions like north, east, south, and west. For sake of teaching and learning the right-hand rule, we're always going to assume that you're facing north. It's not true north, obviously. You might happen to be facing north, but just for sake of teaching, like I always say, the front of the classroom is north. Like we're just going to pretend the front of the classroom is north. Okay, so whichever way you're facing is north, to your right is east, behind you is south, and to your left is west. So we're going to start using northeast, southwest, and then up and down, up away from the ground and down towards the ground. So north, east, south, west, up, down. We're going to have to use all of these words when we're talking about charges moving through Earth's magnetic field and the forces. All right, now let's get into it. Okay, so there's a lot of words in here, but we got this. A proton. Here we go. Proton, that tells me it's a positive charge. Cool. I don't have to flip the direction of my thumb when I'm done. Moves with a speed of that through Earth's magnetic field. Earth's magnetic field has a value of 55 microteslas at this particular location. So the reason we specify that is because Earth's magnetic field fluctuates and changes in time and in space. So it's not a constant, but 55 microteslas is a pretty good working number for the average. Okay, now that's the magnetic field. We don't know the direction just yet. I think we're going to try and find that. What we do know is that when this proton moves eastward, the force is straight upward. Let's stop right there. When the proton moves eastward, the force is straight upward. All right. When the proton moves eastward, so remember, east is to our right. No matter where you're facing, east is to your right, right? North is in front of you. East is to your right, south is behind you, west is to your left. So when the proton moves eastward to our right, so I have to take my right hand and point my fingers to the right. Doesn't matter which way my palm goes. I have no idea which way my palm goes. I just know proton is moving eastward to the right. Then I also know that when that happens, the force, which is my thumb, is upward, not north, not south, up, like towards the roof. So velocity, my fingers point east to my right, check. My thumb, the resulting force we know is straight up, check. So which way is the magnetic field? Whichever way my palm is facing, towards my front, right? What's right in front of me? North. So moving east, if I curl in towards the north for the B field, I get a force that points straight up, check, check. So when the proton moves eastward, the B field points straight ahead of me, which is north, and that gives me a resulting force straight up. Good. Now we were given more information, so let's keep going. So first we were told that when the proton moves eastward, the force is straight up, and that started to tell me that the B field was going to be north. But I have more information. What's the next piece of information that I have? That when the proton moves northward, no force acts on it. Wait, when the proton moves northward, no force acts on it. That means that north is parallel to B. No force acts on it when we move parallel. So again, is the B field in the north? Yes. Is the B field in the north or towards the north? Yes. Both of those pieces of information tells me that the B field is towards the north. Remember that for a cross product, when you move parallel, it's 0. Why? Let's do this. Because the magnetic force, magnitude, is QVB sine theta, where theta is between those two. So if it's moving parallel, theta equals 0. So the velocity was north. Well, let me draw north. The velocity was north. The B field was north. Theta is 0. Sine of 0 is 0. And the force is 0. So check. If the proton is moving northward and the force is 0, that means the magnetic field is northward. So twice, both statements, eastward is straight up and northward is 0. Both of those statements tells me that the direction of the magnetic field is north. Okay? So we're done with part A. And that was just about directionality and the right-hand rule. Now we want to know, what is the strength of the force when that proton moves eastward? And then we want to know for part C, what is the strength or magnitude of that force for the proton, the same proton, moving at 60 degrees north of east? So let's set that up. So first we want to know moving eastward, and then we want to know at 60 degrees north of east. So we want to draw these in terms of our cardinal directions. So we're going to do a standard northeast southwest grid. Northeast, south, west. And nowhere on here is up or down. But up, like towards the roof, this is up. And think of it's the tip of the arrow coming out. And this is down. Think of the back of the arrow. That's just the standard symbols for how we draw vectors that come out and vectors that go in. So up or out of the page. And this is down or into the page. Okay. So what do we have? We have a magnetic field that points north. Okay. So we're going to draw a magnetic field here that points north. And then we have a velocity that points east. So a velocity that points east. So that means that our resultant force comes out of the board. Right? Put your fingers towards the east, towards the right. Face your palm towards north, which is the way you're facing, and your thumb comes out of your page, up towards you. All right. So for part A, we are given that it's a proton. So the mass of a proton, 1.67 times 10 to the negative 27 kilograms. We know the charge of a proton is 1.6 times 10 to the negative 19 coulombs. We were given a velocity of 1 times 10 to the 5th meters per second, and we also know that it is east. And then what else? We were given a strength of the magnetic field of 55 micro Teslas, and we were told that that points north. So the magnitude of what, oh, I'm sorry, this is part B, not part A. So the magnitude of what we're looking for is given by QVB sine theta, where theta is between V and B. So I see that theta is 90 degrees. Sine of 90 is 1. So this is just QVB times 1. Put the numbers in, and we get a magnetic force of 8.8 times 10 to the negative 19 newtons, and that's the magnitude, and we know that it's up. Not north, east, south, or west, but up towards the ceiling. Okay. So let's see. There it is. Part B, check. Part A, check. Part B, check. Okay, let's do part C, where now the same magnetic force, the same speed, The only thing that's going to change is the direction of the speed. We're going to go 60 degrees north of east. So let's just draw that. What does that look like? North of east. So we're going to do the same thing in terms of northeast, southwest. North, east, south, west. And we still have a B field that points directly north. That hasn't changed. But now our velocity points 60 degrees north of east. So north of east. That means start east and go north of that. So start east and go north of that. That's going to be in this quadrant over here. Start east and go north of that by 60 degrees. So that is the velocity. 60 degrees north of east. Okay. So a couple things that we want to do. First of all, let's check the direction again. Well, let's leave the direction for the end. Let's do the math since I have this whiteboard up because I'll lose the whiteboard. So let's just do the math and first find the magnitude. So for part C, we need the magnitude again. And it's still given by QVB sine theta, but my theta has changed. And it's between V and B. So what is theta? It's actually not 60 degrees. It's the remaining 30 degrees, right? It's between V and B, not between V and the eastern axes, but between V and B. Okay, draw it as many times as necessary. My B field goes this way, and velocity goes this way, and the velocity is offset from the x-axis by 60 degrees, which means the angle that I need is 30 degrees between V and B is 30 degrees. All right, so theta is going to be 30 degrees. And nothing else has changed. It's still the charge of a proton. The velocity is still 1 times 10 to the 5th meters per second. And the B field is still 55 microteslas. Okay. And then sine of 30. And we get a magnitude for this, the magnitude of our B field, which is 4.4 times 10 to the negative 19 newtons. That's the strength of it. Okay. So the strength got smaller, because when does it get the greatest strength is when sine of theta equals 1, which is when it moves perpendicular. So anything other than perpendicular is going to give you a smaller force. Okay, but now let's do our directionality. So northeast, southwest is still flat on your table, right? Northeast, southwest will always be flat on the table. We use words like up and down to not be flat on the table. North is straight ahead of you, east is to your right, flat on the table. So let's do this where our velocity is in this manner, 60 degrees north of east, with our B field directly towards the north, so right in front of us. Okay, so still all my directions, northeast, southwest, are flat on the table, up, down. Okay, so instead of having our velocity point directly east, directly to the right, I want to swing it a little bit towards the north, maybe in that direction. So not quite to my right and not quite directly north. But still, My fingers are pointing kind of in this northeastern quadrant, right? North is in front of me, east is to my right. Point your fingers somewhere in this northeastern quadrant. You don't have to be super exact about it. That's for the velocity. And it doesn't matter which way I'm pointing my palm right now, as long as my fingers point in that direction. Okay? In that quadrant 1, if you will. Now, I have to take the B field, and the B field is straight ahead towards my north. Straight ahead towards my north. So now I have to take the palm and face it towards the north, or this is where the curl comes in, or be able to curl your fingers towards your front. Curl your fingers towards your front, because north is towards your front. That's still going to give me a force that points straight up. It doesn't matter if the velocity is east or if the velocity is north of east. As long as I still have to curl my fingers towards my north, that finger's going to point straight up. Okay, so just practice this. Fingers in that northeast quadrant, doesn't matter which way the palm goes. But now I have to be able to curl those fingers towards my front, point my palm towards the front, right? And then curl, and there's my thumb. And if this were an electron, I would do the exact same thing, but then my end result would have to flip. And that's what we're doing next. So let's go back to our slides. So we got these values. We got all three of these values. All three of these values. And in all of these, f of b is up, right? In all of these situations. And the magnetic field is north. Okay, now let's do one more example, but now it's an electron. Okay, so the electron, we're going to have to do the same thing, but at the end of the day, we have to flip our thumb. Whatever result we get is going to be opposite for an electron. Okay, so we have an electron moving in the same magnetic field. So we have a magnetic field that is 55 microteslas north, same magnetic field, moving with the same speed. Okay, but now we've got directionality things to deal with. The speed is going to be 30 degrees south of west, and it's an electron. So first we want to find the magnitude and direction of the magnetic force. Then we want to find the magnitude and direction of the electric force on this electron. Then we want to find the magnitude and direction of the gravitational force on this electron, and then of course the total. Okay, so let's really focus here on this new right-hand rule and cross product. Okay, so let's get a whiteboard and let's write everything we need, everything we have. Okay. So let's see. Let's write down the stuff. We have a magnetic field of 55 microteslas, which is 55 times 10 to the negative 6 teslas north. North. We have an electron, which has a mass of 9.11 times 10 to the negative 31st kilograms. We have the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs, negative. We have the speed of the electron, which is 1 times 10 to the 5th meters per second. And we are told that this electron is moving 30 degrees south of west. So I'm going to start west and I'm going to move 30 degrees south of that. Okay. And then let's see what else. That's it. That's what I need. Okay, so I'm going to start by drawing my grid here. So I need a northeast, southwest grid. North is always the direction I'm facing in this class. That's not true, right? South and west. So my magnetic field, that has not changed. It is still pointing north. Okay, so here's my magnetic field pointing north. Okay, the velocity. It's in that southwest quadrant, that I know. It's south and westish. So I know it's over here somewhere. It's in this quadrant somewhere. That's the velocity. Now I need to figure out where my angle goes. So let's see. It's 30 degrees south of west. So that means start west, and move 30 degrees south of it. So this angle here is the 30 degrees. So the angle between the velocity and the B field, I've got to go all the way around right here. That's my theta between the velocity and the B field. So theta is going to be the 30 degrees plus 90 degrees. They are at 120 degrees from each other. Okay, so let's get a new whiteboard. And let's just work with the magnitude first. We can come back to that whiteboard later. But right now, let's just work with the magnitude. The magnitude says magnitude Q, magnitude V, magnitude B times the sine of theta. And we already know that theta between V and B is going to be 120 degrees. So the magnitude, we're going to talk about direction in a second. Remember, this is all magnitude, so I don't need to put the negative in. 1.6 times 10 to the negative 19 coulombs times 1 times 10 to the 5th meters per second times 55 times 10 to the negative 6 Teslas times the sine of 120 degrees. And this gives a magnitude of the magnetic force of 7.6 times 10 to the negative 19 newtons, right? That's the magnitude. Now let's go to directionality. Okay, so south is towards your back, west is towards your left. So you want to point your fingers kind of towards your left back side, but don't use your left hand. And then you want to turn your palm towards your like right in front of you, and whichever way your thumb points. Okay, so I hope that you're doing this right now as I speak. We're going to do it together. Take your fingers and point them towards your back left side, like someone tapped you over your left shoulder and you're kind of headed that way. Then, how do you get your palm to face towards where, your front is? And your thumb is going to point in a particular direction, which should be pointing down, but it's an electron, so you got to flip it. So the force is still upwards. We're going to do that, but let's just write it down. The magnetic force is up or out of the board. Okay, I'm going to lose the screen once I do it, but that's okay. We have it all written down right here. Okay. It's kind of annoying that I lose screens if I stop sharing, but hey, we do what we do. All right. So velocity has to be, so west is to my left, south is behind me. So that velocity vector was kind of back, like somebody tapped me on this back shoulder, not completely turned around, but kind of towards my left shoulder. Okay. Now I need the B field pointing forward. So I need to figure out how to get my palm to point forward so that I can curl the velocity that comes from the back left forward towards the B field, and that means my thumb is pointing down. So a positive charge would be forced down towards the ground, but this is an electron, so we have to flip our end result. Okay, so do that again. West, south. So southwest. That's how your fingers go. You don't know which direction your palm is going to go. It doesn't matter as long as your fingers are pointing back towards like someone tapped you over your left shoulder. Then your palm has to face north, and this might be a little contortionism. I can't go all the way around. Go this way. Your palm has to face forward so that you can curl it in so that your thumb points down, but it's an electron. Practice that. There's a lot of homework that is just directionality, right hand rule stuff. It's important. Okay. So with our right hand rule, we got that force and we got it pointing up. That force points straight up, not north, not east, not south, not west, like up towards the sky. Okay, now let's work with the electric field. So we have an electric field of 150 newtons per coulomb directed straight down. So we have a magnetic field that points north, which is true in most parts of the earth. It's not exactly true north, but that's a whole complicated issue. And anyone who's ever used a compass and a map knows that you have to adjust your compass. Your compass has to be adjusted to however the map was written. So anyway, it's not true north. North-ish. So magnetic field lines run from our geographic south pole to our geographic north pole. So they point north-ish. But our electric field is downward, not south, but down towards the ground. And we want to find the magnitude and direction of the electric force on this electron. Well, we no longer need velocities, because for electric force, all we need is a charge coming into the electric field. So for part B, for the electric force, all I need to know is the charge and the electric field. It's much easier. So the electric field is 1.6 times 10 to the negative 19 coulombs times the electric field, which is 150 newtons per coulomb. My coulombs cancel. And we get a magnitude of the electric force of 2.4 times, I don't know what the heck that was. That's not a times 10 to the negative 17 newtons. Okay, now what about the direction of the electric field? Well, the electric field points downward towards the ground. A positive charge then, whoops, I wrote this wrong. The electric field points downward. A positive charge then would feel a downward force. Right? A downward force. So that a negative charge is going to feel an upward force. So now, if the electric field points downward, what does a positive charge do? A positive charge would feel a force downward, and a negative charge would feel a force upward. So this is a negative charge, so we get an upward force. All right. So too many screens to work with. So we get upward force, an upward force from magnetism, an upward force from electricity. So physically, this electron is being forced up into our atmosphere, up towards the sky. But now, let's look at gravity. Well, gravity always pushes down. There's no choice on that one. Doesn't matter if you're a positive charge, a negative charge, heavy, light, it doesn't matter. Gravity's always down, period. Like, period. So find the magnitude and direction down, got it, of the gravitational force on the electron. Well, this is just mg. So the force of gravity is just mg. We know m, right? It's a electron, 9.11 times 10 to the negative 31st. And we know g is 9.8 meters per second squared. And bam, we get 8.9 times 10 to the negative 30th newtons downward. So we have a couple competing forces. We've got a downward FB, a downward, whoops, I got those completely backwards. And, an upward, come on, upward FB, upward FE, downward FG, right? So what is the total? Plus, plus, minus, and the total gives us an upward force of 2.48 times 10 to the negative 17. So let's just do that real quick, just to be 100% sure. So I want to write down all my forces just so I have them. So we've got the magnetic force, which is 7.6 times 10 to the negative 19 newtons up. We can go ahead and call that a positive. We've got the electric force, which is 2.4 times 10 to the negative 17 newtons, also upward. Go ahead and call that a positive. We have the force of gravity, which is 8.9 times 10 to the negative 30th, 10 to the negative 30th newtons. And that's down because gravity is always down. So the net force is positive magnetic field, positive force, not field, electric force, negative force of gravity, and the net comes out naturally it comes out to a positive 2.4 times 10 to the negative 17 newtons. And so this positive is what we called up. So we get a net upward force. So this electron is physically feeling a force up away from the ground. And if you look at the numbers, I think it's important to see the numbers on this. The electric force is the largest, followed by the magnetic force, and that gravitational force is way, way smaller. Way, way smaller. And that's why it can have a net upward force. We always think gravity pushes down, gravity pushes down, gravity pushes down. Well, yes, it does. I mean, definitely gravity pushes down, but you have an upward force from electricity, an upward force from magnetism, and a downward force from gravity. But the force of gravity is so small compared to these other two numbers that it really doesn't matter. It's going to feel a net upward force. Okay, so these right-hand rules are not simple, not straightforward. Really good idea to practice them. And remember that it's easiest when you orient yourself so that you're facing north. And we can just always pretend like north is the way we're facing. It's not. I'm actually facing west, almost exactly dead west. But just pretend, hey, that's north. So my right is east, behind me is south, to my left is west. Point your fingers. Let's do this. Let's have an electron. No, let's have a proton moving west. So a proton moving west. So fingers have to point west, left. I don't know which way the palm is going to go yet. Okay, moving west. And then our magnetic field in the earth is going to point north, right? So that means my palm has to point the way that I'm looking. Hey, it's going to feel a downward force. Wait, so a proton moving west feels a downward force, but a proton moving east, here's my proton moving east now, fingers to the right, don't know which way the palm goes just yet. Don't know which way the palm goes just yet, but then I say, wait a second, magnetic field for the earth is north, towards the camera, upward force. Wait, so same electron, same magnetic field. When we move west, no, when we move east, the force is upward. When we move west, the force is downward. Yeah, magnetic forces are a complex thing. And then when we face north, when we're moving north, so fingers towards the north, and then turn your palm towards the north. I can't do that. I can't fit, like, how do, my brain just broke. I don't know how to point my fingers and my palm north at the same time. And if you're struggling, it's because, oh, parallel motion. And the cross product of parallel is 0. So an electron moving, no, a proton moving east with a northward magnetic field, up force. Moving west with a northward magnetic field, down force. Moving north with a northward magnetic field, 0. South, 0. Yeah. Okay, so you have to have some east-west directionality to your velocity if you want to experience a magnetic force in a field that points north-south. Okay, next time, we're done for the day. That's a lot to think about. What we're going to do next time is really explore this mathematical definition of a cross product. So if you've never done a cross product, basically, here's how you do it. Whoa. Here's how you do it, right? If you have done cross products and you want to remember, kind of all the steps to it, go for it. This is a very mathematical definition where there's a negative j hat here, but then I've switched mine to be a positive. So just note that you might have this term and that term reversed. If you've done a lot of cross products in math, you might look at this term and think that it's reversed, but that's because I switched from a negative to a positive. So your choice, if you want to kind of practice your math and do all of your little matrices here, or if you just want to have this written down for our physics class, it's important to know where it came from, but you'll learn that in your math classes. And this is how you find the cross product of two different vectors. We hadn't needed that with problems like this because we just had the magnetic field north, right? But what if I have a magnetic field that has I hat, j hat, k hat components and a velocity that has I hat, j hat, k hat components? Trying to do a cross product of that is, like with my hands, is going to be super complex. So we swing into that highly mathematical mode, okay? So that's what we're going to do next and talk a lot more about these forces. That'll be in part 2. And then we'll come back for part 3 and talk about, wait a second, forces can at moments cause torques. So we're going to talk about how magnetism can create a torque, which is going to open Pandora's box into talking about generators and motors and engines. And motors and engines are not the same thing, and we'll distinguish between them, and generators and all of that. So once we hit magnetism, we finally start getting into the portion, I think, that is a little bit more applicable about electricity and magnetism, actually talking about things like motors, engines, generators, etc., transformers, right? And not like Optimus Prime transformers, but like other transformers. So we're getting to the good stuff, and we're also getting into the good math. Okay, so watch those movies, and I will see you next time. Bye.